Newton carried out the work of Kepler, and in specific, the third law for Kepler. By the time of Newton, there was only force known that is affecting the planets is the centripetal force. And when Newton came and developed all his related equations and universal gravitational law, we discovered that there is a force of gravity that's been defined through the mechanical universe that's been identified using the equations introduced by Isaac Newton. After a lot of investigations and years of research, Newton discovered a bright idea that the centripetal force equals the force of gravity, or the force of gravity is exactly the same as the centripetal force. So when Newton solved this mystery, that helped him to describe better the planetary motion for the planets, and he did mathematical derivation to prove Kepler's third law. The implication of Newton's work was huge because scientists now had the mathematical tools necessary to explore the solar system in more details. If we have a satellite that's following his path around the Earth, and let's say we need to find the speed of that satellite, we know the satellite is at a certain distance from the Earth center. We can use the equation v as the velocity or the speed of satellite equals the square root of the gravitational constant by the mass of the Earth over r. If we take an example on that, let's say the Earth's moon is 3.844 by 10 to the power of 5 kilometers from Earth. That is your r. Determine the orbital speed of the moon. Of course, if this was a satellite, same concept, either planet, moon, any object at this distance, you have his mass, you have the distance center to center from Earth, you can find the speed of that object. So we have the r, and we can use the equation v equals square root g m Earth over r. That would give you the velocity of the moon of 1.02 by 10 to the power of 3 meters per second. And that would be the orbital speed of the moon, that is either in meters per second or in kilometers per hour. Another example, let's say we have a Landsat, is an Earth imaging satellite that takes picture of Earth ozone layer and geological features. It orbits around the Earth on a height of 912 kilometers. What are its orbital speed? And it is period. So we're given the height of the satellite above the Earth. And if you take that height and you add it to the distance from the surface of Earth to the center of Earth, which we know, that would give you the radius between the center of the satellite and the center of Earth. And it's become like the same example as the Moon-Earth problem. We need to find V and T. We found the R by adding the R Earth from surface to center of Earth plus the height of the satellite, or how far from the surface of the Earth. That gave you the R. We know that the F centripetal equals the F gravitation. F centripetal is the mass of satellite by V squared over R equals gravitational constant by the mass of satellite and mass of Earth over R squared. V would be this, and if you replace all the given inputs, that would give you the velocity of that orbital satellite would be 7.39 by 10 to the power of 3 meters per second. To find the period that he asked for, we know period equals 2 by r over v in this case. 2 pi multiplied by 7.292 by 10 to the power 6 meters over the v, which we found earlier, 7.39 by 10 to the power of 3 meters per second. That will give you the period of 6.2 by 10 to the power of 3 seconds. Sometimes you would have the speed of the planet, the distance from the other planet, let's say the distance between Moon and Earth, and you need to find the mass of that planet from those given inputs. Now, if that's the case, we keep in mind that the F centripetal equals Fg, and if you rearrange the two equations, F centripetal would equal 4 pi squared m the moon multiplied by r over t squared of the moon. M of the moon is the mass of the moon in kilograms, t of the moon is the period of the moon in seconds. Equalizing those two equations would give you the mass of Earth, if you are looking for the mass of Earth, would be 4 pi squared r cubed over t squared moon by g. Now the mass of Earth would equal, by plugging in all these given numbers, 6.04 by 10 to the power 24 kilograms. Quick summary for this chapter. Key terms we talked about is the axis of rotation, cycle, revolution, period, frequency, RPM. We talked about centripetal forces, centripetal acceleration, uniform circular motion. We discussed thoroughly the Kepler's laws and how they came, and we talk a little bit about the elliptic paths of the moons in their orbits, eccentricity, orbital period, orbital radius, satellites finding their speeds and mass in the orbit. The key equations we discussed: V equal 2 by R over T, A centripetal 4 by squared R over T squared, TA squared over R cubed, A equals TB squared over RB cubed, A centripetal equals V squared over R, F centripetal MV squared over R. So you can take a screenshot of this summary and keep it for your reference. You can use it in your exams. You can use it for your future problem solving or even real life problem solving that you may need, and you'll find it handy for you.